The cosmos is an endless stage where, in an infinite dance of matter, stars and planets are formed. Young Earth, as a fragment of this grand symphony, was born in a swirl of cosmic dust and gas, which coalesced into vast clouds. Imagine that we are witnessing a moment when, in one part of the galaxy, amidst the bright flashes of newborn stars, a small clump of matter begins to gather under the influence of gravity. This process is not merely the touch of matter, but an entire epoch spanning billions of years, a time frame that is difficult for human reason to comprehend. Molecules collide, forming more complex compounds, as if we are watching individual musical notes combine into a symphony. Gradually, under the influence of heat generated by these collisions, materials melt and then solidify, forming the substances that will make up our planet. In this process, continents and oceans are formed, like a sculptor carving a figure from marble that is yet to know its destiny. The scale of time here is not just immense, it is almost inconceivable. Millions of years pass like a single moment, and in this endless flow of time, simple chemical elements transform into complex structures that will eventually form the basis of life. Earth, surrounded by clouds, begins to cool, and in its depths a core starts to form, which later will become a magnetic shield protecting life from cosmic radiation. This time is like a vast canvas on which nature paints its masterpieces, and each new era brings its changes. Each new phenomenon is a step towards a future that is still impossible to imagine. At this moment, on a land where not a single living being exists, an atmosphere is forming that will sustain life, and on the horizon, the first molecules of water appear, ready to become oceans that may one day witness the first steps of humanity. Earth begins to rotate around its axis, and this process, unfolding against the silent backdrop of the cosmos, is like a theatrical performance that will unfold over billions of years, when the voice of humanity will echo across its surface. Enormous forces acting within the planet cause volcanic activity, spewing lava that forms mountains and valleys, and in this chaos, beauty is born, which will inspire future generations. Time here is not just a measure, but a living entity that defies human control, and each second is a new opportunity, a new probability, which unfolds into an endless web of events from which life will one day emerge. In the early stages of the formation of the solar system, approximately 4.5 billion years ago, a moment occurred when a cloud of cosmic dust and gas began to rotate around the young sun. This cloud, known as the solar nebula, was primarily composed of hydrogen and helium, and also contained heavy elements formed during previous generations of stars. Under the influence of gravity, particles began to approach each other, forming a protoplanetary disk that gradually became denser. The temperature in this disk varied greatly. It reached thousands of degrees Celsius near the sun and could drop to a few tens of Kelvin in distant regions. This contrast created conditions for the formation of various materials. Metals and rocks condensed near the star, while gases remained in more distant areas. In this magnificent cosmic dance of matter, particles rotated, collided, and combined, creating not only planets but also moons, asteroids, and comets. The brightness of the young sun illuminated the disk, contrasting with the boundless black cosmos and creating a captivating spectacle. The spectrum of light varied from bright yellow and white hues to deep reds, depending on the temperature and composition of the particles. Each rotation of the disk was slow but inevitable, continuously forming new structures that would eventually become the foundation for the formation of planets. As particles collided and combined, energy was released, increasing the temperature and brightness, creating almost a magical atmosphere. These processes took millions of years, but in cosmic terms it was just a moment. At the center of this wonderful process was the young sun, which gradually became hotter and brighter, causing the surrounding disk to glow and sparkle. These dynamic changes in the protoplanetary disk led to the formation of the first solid bodies, which later became the basis for the planetary system. The formation of planets like Earth occurred through accretion, a process in which small particles accumulated to form larger bodies, accompanied by powerful collisions that further contributed to their development. It is important to note that this process was not uniform. Different parts of the disk had unique characteristics that influenced the speed and manner of planet formation. For example, Jupiter, the largest planet in our system, demonstrates how its massive gravity could capture a large amount of gas, making it a gas giant. Thus, the protoplanetary disk was not just the birthplace of planets, but also the stage for complex interactions of matter that determined the future of the entire solar system. As a result of these processes occurring over millions of years, the main elements of the system, including planets, their moons, and numerous small bodies, such as asteroids and comets, were ultimately formed. The process of accretion is a slow and majestic dance of cosmic particles that begins with tiny dust motes wandering through the boundless expanse of space. Complex interactions between molecules create conditions that allow these motes to collide, stick together, and form larger objects, which over time become pebbles. This process is not instantaneous. It unfolds over millions of years, evoking a sense of endless time. For instance, according to astronomer Dr. Linda Spilker of NASA, accretion in the protoplanetary disk around a young sun took place over approximately 100 million years. In each such collision, which in reality occurs at a speed of just a few centimeters per second, dust motes interact, forming tiny aggregates that then continue to coalesce. Imagine this process. Minuscule particles, like dancers, slowly approach each other and finally unite in a tender embrace, creating new structures. These collisions occur in the dark void where each moment can feel like eternity, and movement is almost hypnotic. With each new union, pebbles form, growing in size and eventually becoming asteroids, comets, and other celestial bodies. Research shows that even the smallest particles have a chance of sticking together if they possess sufficient gravitational attraction. For example, particles a few microns in size can form larger aggregates that can reach several meters in size. This accretion process, occurring over millions of years, forms the basis for the subsequent creation of planets and other large celestial bodies. It is not just random collisions, but a complex system of interactions where each particle plays its role in creating larger structures. Ultimately, it is accretion that drives the formation of planets, as it did with Earth, which formed around 4.5 billion years ago. Formation of planetesimals, the first large bodies in the protoplanetary disk, became a crucial stage in the evolution of our solar system. Approximately 4.5 billion years ago, when the temperature in the cloud of gas and dust from which the solar system emerged began to decrease, small particles started to stick together, forming larger objects up to kilometers in size. These planetesimals were piles of rocky materials orbiting the Sun. Gravity, acting as an invisible hand, began to play an increasingly significant role, attracting more material to the already formed centers. At this time, the cosmic space resembled a giant marble hall filled with thousands of rocky bodies, each with a unique shape and size, from small pebbles to massive monsters tens of kilometers long. These bodies, colliding with each other, caused powerful explosions, resulting in the formation of larger objects that eventually became protoplanets. Imagine this emptiness, where absolute silence reigns and collisions occur that change the fate of these celestial bodies. Microparticles, initially scattered, gradually transformed into larger structures, creating internal processes that would determine their future. This process was not just random. It was driven by gravitational interactions acting like magnets, attracting more material. Ultimately, after millions of years, these planetesimals became the primary building blocks for the formation of planets like Earth, and their role in this process cannot be underestimated. Gravity, initially just one of the factors, soon became the dominant force, shaping the landscape of our solar system. And despite the vast distances, these rocky bodies created a network of interactions that led to the formation of planets. At this stage, the cosmos was filled with silence, but processes were taking place that would create conditions for the emergence of life in the future. Collisions between planetesimals sometimes triggered chain reactions, where new bodies formed and old ones were destroyed. These events occurred over distances measured in millions of kilometers, but their influence was felt everywhere. Surrounded by emptiness, these objects, like sculptures, were formed and changed, their fate depending on random encounters and gravitational interactions with neighbors. Ultimately, these rocky bodies became the foundation for the formation of new planets and moons that we know today, and their influence on the formation of the cosmic landscape continues to be of interest to astronomers and historians of the cosmos. During the formation of proto-Earth, numerous planetesimals, which were small but massive icy and rocky bodies, gradually merged to form a larger body. These planetesimals, ranging in size from several meters to tens of kilometers, collided with each other, creating powerful explosions and ejecting materials into space. Each new impact added material to the existing masses, causing the gradual growth of proto-Earth, as if it were awakening from a long sleep. At this stage, there was no atmosphere, no oceans, only hot magma and debris orbiting around the formed core. This slow process took millions of years, creating a sense of cosmic tranquility and inevitability, as if the entire universe was watching the development of its new daughter. As the body grew, gravity exerted an increasing influence, attracting more planetesimals, which, like meteors, flew through the dark expanse of space to become part of this young planet. Simultaneously, processes of differentiation occurred, with heavier elements such as iron and nickel settling in the center to form the core, while lighter elements rose to the surface, creating mantles and crust. This process was not just physical, it also involved changes in chemical composition, which would later determine the future of our planet. Throughout this time, proto-Earth was subjected to constant bombardment by meteoroids, which added new mass and altered the surface, creating relief that would later form the basis for continents. As mass accumulated and temperature increased, aggregation of particles and materials occurred, facilitating the formation of the first minerals and rocks on the surface. In this slow but inexorable process of proto-Earth formation, each step was crucial as it determined not only the physical state of the planet but also its future as a home for life. This sequential aggregation of matter and energy released from collisions created conditions for the formation of the first oceans, as the surface temperature began to decrease, paving the way for further development of the atmosphere and hydrosphere. At this stage, a new era began, when proto-Earth finally began to acquire the features we know today. There is evidence that during this time, primary oceans could have formed on the surface of proto-Earth, consisting of vapors that condensed into water, which was a crucial stage in the development of conditions necessary for life. Modeling these processes shows that it was this long-term aggregation and sustained development that led to the formation of the planet we now know as Earth. The hypothesis of a giant collision with the protoplanet Theia suggests that around 4.5 billion years ago, two large celestial bodies, one of which eventually became Earth, were slowly approaching each other in the boundless cosmos. This approach occurred in the silence of the void, where speeds of movement were in the tens of kilometers per hour. The protoplanet Theia, with a size comparable to Mars, was a massive body composed of molten rocks and metals moving towards Earth along its orbit. At the moment of impact, when the two planetary giants met, a cataclysmic event occurred, a majestic cosmic phenomenon that can be compared to a grand dance of destruction and creation. The impact created powerful waves of molten material that erupted into the Earth's vicinity, forming clouds of gas and dust that gleamed in the dark expanse of the cosmos. This ejection of material became the basis for the formation of the Moon, as lighter elements began to accumulate in one place under the influence of gravity. Research shows that the temperature at the moment of impact reached several thousand degrees Celsius, leading to the instantaneous melting of a significant part of both bodies. Scientific works, such as those conducted by astronomers from the Massachusetts Institute of Technology in 2008, confirm that this cataclysm was a turning point in the evolution of our planet. As a result, a vast cloud of debris formed around Earth, which later condensed and became the Moon, a satellite that has since influenced numerous processes on Earth, including tides. Thus, this collision not only changed the appearance of the planets, but also became the starting point for the formation of conditions necessary for life. The Moon, located at a distance of approximately 380,000 kilometers from Earth, plays a key role in stabilizing the planet's axis of rotation, which in turn affects climatic conditions over millions of years. As a result of a powerful collision that occurred approximately 4.5 billion years ago between young Earth and a Mars-sized planet known as Theia, a vast amount of debris was ejected into space. This debris, primarily composed of silicate and metallic materials, began to orbit Earth, forming a disk of particles. This process was not instantaneous. It took several tens of millions of years, during which small fragments of matter gradually drew closer to each other under the influence of gravity. Imagine tiny dust particles spinning in the emptiness of space amidst meteor showers and residual gases slowly attracting each other and forming larger clumps. Over time, these clumps combined to form larger bodies, which in turn attracted smaller fragments, continuing until a single large object was formed, the Moon. This assembly process was majestic. Over millions of years, scattered and chaotic particles began to take on more defined shapes, eventually coalescing into the sphere we know today. Initially, this was a molten mass, but over time, as it cooled, craters and other geological formations began to appear on the lunar surface. Simultaneously, numerous collisions with other meteoroids left their marks on the surface. In this cosmic expanse, a sense of calm prevailed despite the chaos, and gradually, over a long period, the Moon acquired its stable orbit around Earth, becoming the celestial body that watches over us. Ultimately, the Moon became not only an object of study, but also a crucial element in the system that influences the tides on our planet. After the formation of Earth, approximately 4.5 billion years ago, the planet was a completely inhospitable place. It was a molten sphere of magma, heated to such temperatures that all matter on its surface turned into liquid rock. The surface glowed brightly and dazzlingly as if the Earth itself was a giant fiery lamp casting light on endless waves of magma. These waves, resembling ocean waves, gently rolled across the surface, creating the illusion of movement in an ocean of fire that seemed to never fade. In this inferno, there were no familiar landscape elements, no mountains, no seas, no rivers. The entire surface was covered in liquid magma which boiled and churned like in a giant cauldron. High temperatures and pressure created conditions where any familiar minerals and elements, such as silicon or oxygen, existed only as atoms, waiting in line to form more complex compounds. There was no solid crust, and the entire planet resembled a giant volcano ready to erupt at any moment. This chaos lasted for millions of years until the first solid formations began to appear. However, before this point, Earth was an endless ocean of fire where life as we know it was still a distant dream. Ultimately, this primitive atmosphere filled with vapors and gases created conditions for the emergence of the first molecules capable of self-replication. The entire scene could have seemed horrifically beautiful if it were not for the realization that beneath this fiery ocean, the world was just beginning to take shape. The anticipation of the formation of a solid crust when the planet finally cools, and the possibility of something new emerging left a sense of inevitability in the air. On the surface of early Earth, a magma ocean reigned, a churning and glowing mass of molten rock. There was not a hint of land, only massive waves of magma rose and fell, creating constant motion, reminding us that Earth was still in its youthful phase. The temperature of this magma reached incredible 900 degrees Celsius, and it sparkled in various hues, from bright yellow to deep red, creating a spectacle that could have astounded even the most seasoned time travelers. In some places, magma erupted to the surface, spewing even hotter material from the planet's depths. Upon contact with the cold gases of the atmosphere, it formed clouds of steam and dust, adding to the chaos and visual diversity. These eruptions could reach heights of up to 5 kilometers, making them visible from a distance. Whirlwinds of molten rock rose into the air, as if the planet itself were breathing, emitting sounds reminiscent of heavy blows. Each such moment was part of the grand process of Earth's formation, as chemical elements combined to eventually form minerals and rock. Around 4 billion years ago during this period, the first continents began to form as magma cooled and solidified into a hard crust, which would later become the foundation for all life on the planet. But while the magma ocean was still in its prime, Earth's surface resembled a giant frying pan where molten masses boiled and bubbled, and each wave brought forth new elements for the future geological history. Thus, in this dark yet captivating environment, the conditions began to form that would eventually give rise to life. The process of differentiation of the Earth's material occurred during the formation of the Earth, which began approximately 4.5 billion years ago. At that time, the planet was in a state of molten ocean, where the materials were in a chaotic state. Heavier elements, such as iron and nickel, began to slowly sink towards the center of the planet under the influence of gravity, forming the core. This process was not instantaneous. It took millions of years, comparable to drops of wax slowly flowing down and forming a stable structure. Lighter elements such as silicon, oxygen, aluminum, and magnesium rose to the surface, forming the mantle and crust. Studying this process, scientists like geologist David P.M. Goodwin discovered that as a result of differentiation, a clear boundary formed between the core and the mantle, determining the internal structure of the Earth. The core, consisting mainly of iron and nickel, has a radius of about 3,200 kilometers and a temperature reaching approximately 5,000 degrees Celsius, comparable to the surface temperature of the Sun. Meanwhile, the mantle, consisting of molten and semi-solid rocks, extends to a depth of 2,900 kilometers, representing a complex layer where convective flows occur. These flows, similar to giant vortices, move matter, contributing to the formation of tectonic plates, which ultimately determine the landscape of the Earth. In other words, it was this process of differentiation that created the conditions necessary for the formation of continents and oceans, as well as for the emergence of life on the planet. This slow but inexorable process of changing the internal structure of the Earth demonstrates how dynamic and complex the process is occurring even in the depths of our planet are. The formation of Earth's iron core began approximately 4.5 billion years ago, when the planet was still forming from a gas dust cloud. During the process of accretion, heavy metals, primarily iron and nickel, gathered in the center of the Earth, creating a dense metallic core of our world. This occurred due to gravity. Heavier elements were drawn to the center, while lighter materials remained closer to the surface. Imagine a massive sphere of molten metal pulsing at the very center of the planet, with temperatures reaching over 4,000 degrees Celsius. This process was not only physical but also chemical. High temperatures and pressures facilitated the formation of various alloys, in which iron and nickel formed unique combinations. Research has shown that this iron core consists of two parts, an inner solid core and an outer liquid core. Data on the core's composition have been obtained through seismic studies, which have shown that seismic waves passing through the Earth behave differently depending on the state of the material they pass through. These data have allowed scientists such as seismologist Rainer Grunzweig to determine the core's main characteristics. The outer core plays a crucial role in the formation of Earth's magnetic field, although its exact mechanisms are not yet fully understood. However, it is known that the movement of liquid iron in this layer generates electric currents, which in turn produce the magnetic field. This field protects Earth from solar wind and cosmic radiation, which is of critical importance for the existence of life on the planet. As Earth cooled, the inner core gradually increased in size, creating conditions for the emergence of complex geological processes on the surface. These processes, such as plate tectonics, are directly linked to the dynamics in the core, where temperature and pressure remain at extremely high levels. Thus, the iron core not only formed during the process of accretion, but also became an essential element in creating the conditions necessary for life on Earth, providing protection from external influences. The cooling of Earth's surface, which began approximately 300 million years after accretion, resembled the cooling of a hot drink in a cup. The magma ocean gradually lost its temperature, slowly transforming from a molten mass into something more stable. Initially, this ocean covered the entire planet, and its surface temperature was so high that water existed only in vapor form. Gradually, as the temperature began to decrease, the first solid crusts formed on the surface, which later became the basis of Earth's crust. This crust, like the fragile shell of an egg, was extremely thin and unstable. Its thickness could be estimated at only a few kilometers, making it vulnerable to various geological processes. Constant tectonic movements, volcanic activity, and collisions with other celestial bodies continually destroyed this initial crust, forcing it to regenerate through new cooling and solidification processes. For example, during the Archean Eon, which began around 4 billion years ago, numerous catastrophic events occurred on the planet, leading to the formation of new crustal areas, while older ones continued to be destroyed. Notably, it was during this period that the first continents formed, which later became the foundation for further geological development on our planet. There was a constant struggle between processes of destruction and formation, creating a sense of unstable equilibrium in which the young crust tried to maintain its integrity despite constant external challenges. This fragile structure that emerged on Earth's surface served not only as the basis for future ecosystems, but also as a platform for the development of the first forms of life, which began to appear after millions of years. Nevertheless, each new formation of crust was accompanied by inevitable changes that could lead to its complete destruction due to volcanic activity or asteroid impacts, highlighting the fragility and dynamism of this process. Ultimately, it was this instability and constant changes that gave Earth its unique appearance, which we observe today. As a result, even the earliest stages of crust formation became the foundation for a complex journey that led to the emergence of diverse ecosystems and life forms, opening interesting horizons for the study of our planet's geological history. During the Archean Eon, numerous significant changes occurred, each contributing to the creation of the complex system that is now known as Earth. At the dawn of Earth's formation around 4 billion years ago, the primary solid crust was a dark, basaltic surface that underwent constant changes under the influence of volcanic activity. This crust was thin, like an eggshell, and floated on the surface of still molten mantle, which ignited life on the planet. Imagine the scene: black patches of solidified rock, resembling endless lava fields, starkly contrasted with bright, glowing fissures where magma, heated to thousands of degrees, rose from the planet's interior. These fissures, like wounds on Earth's body, spewed lava that, cooling, formed new crustal areas, creating a cycle of destruction and restoration. Meanwhile, volcanoes, like giant torches, illuminated the night sky, ejecting clouds of ash and gases that, in turn, formed an atmosphere rich in carbon dioxide and water vapor. This was a planet where every second could change. Lava outflows created new land areas, while strong earthquakes tore the crust, allowing magma to rise. Scientific research conducted at the beginning of the 21st century revealed that it was during this period that continents began to form, as the crust cooled and thickened, gradually forming the first stable lands. Scientists like Dr. James Stewart from Cambridge University assert that these early continents were smaller than today's, consisting of numerous small segments that later merged. As a result of this process, the planet's first shores emerged, where oceans, rich in minerals, interacted with the solid crust, creating conditions for future life. These primeval oceans, filled with nutrients, became an ideal environment for the emergence of the first microorganisms, which became the ancestors of all life on Earth. Volcanic activity not only shaped the landscape but also influenced the climate, creating sharp temperature fluctuations and conditions in which life could either thrive or perish. Against this backdrop, conditions were formed for a new era when the first chemical reactions began, leading to the formation of organic compounds. Despite its fragility and susceptibility to fractures, as evidenced by samples of rock studied by scientists in various regions of Earth, including Greenland and Canada, the ancient Earth's surface was not only active but also dynamic, with constantly changing conditions that gave our planet its unique appearance. In the early stages of Earth's formation around 4 billion years ago, the planet was covered with thousands of active volcanoes that spewed lava, gases, and ash into the atmosphere. These volcanoes, similar to colossal chasms, shook the surface, creating rivers of molten rock that flowed across the young continents, forming new landscapes. Volcanologists like Dr. David Cliff from the University of Washington note that during this time, volcanic activity never ceased, creating ideal conditions for the formation of the first continents and oceans. Fountains of magma erupted from the Earth's interior, creating fiery columns reaching heights of up to 10 kilometers. Thus, the horizon constantly flickered with the brightness of eruptions, reminding us that Earth was in a state of constant change. Volcanic gas emissions consisting of water vapor, carbon dioxide, and sulfur contributed to the formation of an atmosphere that was far from what we are familiar with today. These processes led to the formation of vast volcanic plateaus, such as the Siberian platform, where layers of volcanic deposits reached depths of more than 2 kilometers. Volcanic eruptions had a colossal impact on the climate, releasing millions of tons of ash and gases into the atmosphere, which could cause temporary cooling events known as volcanic winters. For example, the eruption of the Toba volcano in Indonesia, which occurred around 70,000 years ago, released so much ash that it could significantly affect the global climate system. Meanwhile, these volcanic events served as a source of mineral resources such as gold, copper, and other metals that formed as a result of the cooling of magma. Volcanic activity also contributed to the formation of the first living organisms, as minerals and chemicals from magma became the basis for the appearance of simple life forms. These processes were not just random events, they shaped ecosystems that, in the end, became the foundation for more complex forms of life. With each new eruption, Earth became more diverse and complex, and its appearance changed before our eyes. For example, research conducted in the 18th century showed that layers of volcanic ash could provide clues about how the climate changed in different historical periods. Volcanic activity not only shaped landscapes but also the biosphere that existed on the planet. Early Earth's atmosphere, which existed around 4 billion years ago, was a dense and opaque shroud of gases that enveloped the planet like a heavy blanket. This was a time when Earth was still forming, and its surface was filled with volcanic activity, spewing toxic gases into the atmosphere. These gases, emanating from the planet's interior, created an atmosphere completely inhospitable to modern living organisms. Unlike the clean and transparent air we breathe today, this atmosphere had a dark and oppressive appearance. Complex volcanic processes led to the formation of clouds of sulfur gas and other toxic substances that filled the sky and blocked out sunlight. Surface temperatures could reach extremely high values, often exceeding 100 degrees Celsius, creating conditions in which life, as we know it, would be impossible. Volcanic eruptions, such as those that occurred in the region of today's Hawaiian archipelago, released vast amounts of lava and ash, further exacerbating the situation. These factors together created an atmosphere dominated by gases capable of causing serious chemical reactions but unable to support life as we understand it. Over time, as a result of various geological and biochemical processes, the atmosphere began to change. The appearance of the first microorganisms capable of photosynthesis became a turning point, altering the atmosphere's composition and preparing the ground for the emergence of more complex forms of life. Scientists such as Professor David Grinspoon from the Planetary Science Institute argue that these microorganisms began to release oxygen, which gradually displaced toxic gases, creating conditions for the existence of more complex ecosystems. This process, known as the oxygen catastrophe, occurred approximately 2 billion years ago and marked a pivotal moment in Earth's history. Therefore, early Earth's atmosphere was not only toxic and opaque, but also played a crucial role in shaping the future appearance of our planet. Volcanic activity not only created the first breathable conditions, but also set the course for the evolution of life, which subsequently filled the oceans and land masses. In the early days of Earth, a meteorite bombardment took place, creating a scene where the sky was crisscrossed with glowing trails of falling bodies. These celestial bodies, ranging from small meteoroids the size of grains of sand to massive asteroids with diameters of several kilometers, relentlessly pounded the planet's surface. Approximately 4 billion years ago, during a period known as the Epoch of bombarding, Earth was subjected to this process with such intensity that craters formed wherever any cosmic body could reach the surface. For example, the Wilkett crater in Australia, with a diameter of around 14 kilometers, was formed as a result of a meteoroid impact that occurred on Earth about 300 million years ago. But this is just a drop in the ocean among countless other craters, such as the Tycho crater on the Moon, which also attests to the scale of this cosmic rain. Each impact left behind not only craters but also altered climatic conditions, creating clouds of dust and debris that then settled on the surface, forming new geological layers. According to scientists' estimates, during the first 100 million years after Earth's formation, the planet could have been struck by cosmic objects every few tens of thousands of years, with some of them being large enough to cause global catastrophes similar to those that could have wiped out entire species from the face of the Earth. These events vividly underscore that Earth was under constant attack from space, and the sky, strewn with meteors, was not just a beautiful sight, but an integral part of the planet's formation. Meteoroids not only introduced new elements into the planet's chemical composition, but also created conditions for the emergence of the first bodies of water, and, possibly, even for the origin of life. A significant aspect of the meteorite bombardment is that it contributed to the formation of various minerals and compounds that later became the basis for the formation of soil. Meteoroids containing water could have introduced necessary components into Earth's atmosphere, influencing the formation of the first oceans. Events such as the Chicxulub meteorite impact in Mexico, which occurred around 65 million years ago and led to the extinction of dinosaurs, demonstrate how catastrophic the influence of space can be on life on Earth. All this meteorite activity not only created physical changes but also geological dynamics that we can observe today in the form of diverse landforms and minerals on the planet's surface. Approximately 4 billion years ago, Earth experienced one of the most catastrophic periods in its history, known as the Late Heavy Bombardment. During this time, the number of asteroids falling on the planet sharply increased, and their impacts left no chance for a peaceful existence for the young Earth. According to scientists, this period, lasting around 100 million years, saw the fall of enormous celestial bodies onto the planet, some of which were comparable in size to modern countries. For instance, asteroids over 100 kilometers in diameter struck the surface, creating craters as large as entire megacities and causing global catastrophes. The impacts were so strong that they melted the already solidified crust, creating new magmatic rocks and altering the planet's geological structure. One of the most famous such collisions occurred around 4 billion years ago, resulting in the formation of the Ries crater on the Moon. This crater, with a diameter of around 1,200 kilometers, is one of the testimonies of the cosmic activity that prevailed at that time. NASA scientists have estimated that more than 100,000 objects may have fallen on Earth during this period, each leaving its mark in the form of craters and new geological formations. This bombardment not only shaped the planet's landscape but also influenced the climate by releasing vast amounts of dust and gases into the atmosphere, potentially causing sharp temperature changes. All this happened on a planet that was already formed but still extremely unstable, with conditions for life far from ideal. Asteroid impacts caused massive tsunamis, and volcanic gas emissions could lead to acid rain, further complicating the existence of any forms of life that might have tried to emerge. Thus, it was during this period that Earth laid the foundations for its further development, facing colossal cosmic threats that shaped its future. Scientific research, such as the work of a group of geologists led by Dr. John Brown of the University of California, shows that this epoch gave impetus to the formation of the first oceans, as greenhouse gases released during impacts began to condense, forming water masses. Amid these cosmic catastrophes and transformations, Earth, like a young warrior, endured and continued its journey into the boundless cosmos. During the formation of Earth, a significant role was played by meteorite bombardment, which supplied the planet with the necessary water reserves. Starting around 4 billion years ago, icy comets and asteroids containing water rained down on its surface. Scientists estimate that approximately 70% of all the water on Earth could have been delivered by such celestial objects. Comets, primarily composed of ice and dust, served as true cosmic messengers. Upon entering the atmosphere, they burned like fiery arrows, leaving behind bright tails and eventually colliding with Earth. For instance, Comet Hale-Bopp, visible in the 90s, consists of about 80% ice. Upon impact, these comets and asteroids released water from the crystalline lattice of ice, converting it into liquid over the course of millions of years. Asteroids like Ceres contain hydrated minerals, further supporting the theory that they could have been a source of water for Earth. Moreover, researchers have found that there are many such objects as Ceres in the asteroid belt, and their impact on young Earth was constant. This process was gradual, drop by drop, meteorite by meteorite, forming the future water reserves of the planet, which became the basis for the emergence of life. Scientific research shows that within 1 billion years after Earth's formation, there was enough water to form oceans. Over time, as vast reserves of water accumulated, the planet began to resemble the blue planet we know today. And life, as we know it, became possible precisely due to this delivery of water from space. The formation of the primary oceans on Earth was the result of a complex process that spanned millions of years. In the early atmosphere of the planet, rich in water vapor, the temperature was so high that the vapor remained in a gaseous state. However, as the Earth cooled, the temperature began to gradually decrease, and the water vapor, unable to remain in the air, started to condense into water droplets. This process can be imagined as enormous rains that did not last for days or even years, but stretched over thousands of years, turning the atmosphere into a real ocean of clouds. The water falling onto the surface of the hot planet filled the low-lying areas in the relief, forming the first seas and oceans. Over time, these rains created water basins that gradually expanded, connecting with each other until they formed vast water expanses that we know as oceans. Each millimeter of precipitation, each moment of these rains added new volumes of water to the already formed water bodies, while the hot surface of the Earth facilitated evaporation, creating a closed cycle that kept the atmosphere saturated with moisture. This process of ocean formation was fundamental for the emergence of life, as it was in these waters that the first primitive organisms began to appear. The complex dynamics of ocean currents, which began to form under the influence of wind and the rotation of the planet, also played a crucial role in the even distribution of heat and nutrients in these primary water bodies. These ancient oceans, with their high temperature and mineral richness, became the cradle for the first forms of life, which began to evolve in conditions that were completely unlike those of today. The water that filled these oceans was not just H2O, but a carrier of numerous chemical elements necessary for complex biochemical reactions that became the basis of life on Earth. Thus, the formation of the primary oceans was not a random event, but the result of a long and complex interaction between the atmosphere, geology, and climate of the Earth. This long history of ocean formation provides a multi-layered context for understanding the further development of life on the planet. Ultimately, millions of years of rain created the foundation on which the entire biosphere developed. The first rains on Earth, which began approximately 3.5 billion years ago, were nothing like the familiar rainfall we experience today. These rains were not pure water, but rather acidic flows rich in chemical compounds such as sulfuric and carbonic acids. Imagine a young planet with a surface temperature exceeding 300 degrees Celsius, where constant volcanic eruptions released vast amounts of gases into the atmosphere. At this moment, a continuous downpour fell from the sky, capable of transforming the entire planet. The downpour consisted of droplets that, upon hitting the scorching rocks, hissed, and each droplet turned into clouds of steam rapidly rising into the atmosphere. This process created a breathtaking spectacle where the forces of fire and water clashed. When the droplets encountered hot surfaces, they did not simply flow but roared as they evaporated, releasing steam laden with chemical elements that could then interact with each other. These early rains not only shaped the planet's landscape, but also contributed to the creation of conditions favorable for further life development. Gradually, the acidic rains leached minerals from the rock formations, turning them into nutrients for future organisms. This was a true cataclysm that in turn created new ecosystems. The chemical reactions caused by these rains played a crucial role in the formation of the primary oceans, where life eventually emerged. Each such rainstorm can be compared to a giant cauldron where elements necessary for the formation of the first simple organisms were mixed. As a result of this endless cycle where rain fell repeatedly on the planet, not only oceans but also the atmosphere formed, capable of supporting life in the future. It is hard to imagine how powerful this spectacle was, water falling from the sky on one side and scorching rocks on the other, creating a sense of constant struggle between the elements, where nature sought to find balance in conditions that seemed utterly intolerable. In these conditions, the foundations for complex biochemical processes were laid, which later became the basis for the emergence of the first living organisms. The first bodies of water on early Earth were vastly different from today's oceans. These primary seas, which emerged around 3.5 billion years ago, were hot and rich in various minerals, creating conditions that seem extraordinary by today's standards. The water in these bodies had high temperatures, often exceeding 60 degrees Celsius, which facilitated the formation of steam that actively evaporated from the surface. This led to the atmosphere being saturated with water vapor, creating the greenhouse effect. The colors of these bodies of water ranged from murky greenish-brown to vivid pink, due to high concentrations of iron and other minerals that gave the water unusual hues. These seas were not static. Their boundaries constantly changed due to continuous volcanic activity and changes in the planet's topography. Volcanic eruptions released large amounts of soluble gases and minerals into the water, raising the acidity level and creating complex chemical reactions. For instance, in some areas, mineral deposits such as stromatolites formed, serving as shelters for the first microorganisms. These ever-changing conditions necessitated a constant struggle for survival, shaping unique ecosystems. Research indicates that in these bodies of water, microorganisms capable of using chemical substances for energy existed, which preceded the emergence of photosynthesis. Volcanic islands that appeared on the surface served as temporary sanctuaries for the first forms of life seeking stable conditions for reproduction. The boundary between sea and land fluctuated constantly, creating new ecosystems that could only thrive for a short period before the next eruption or climate change destroyed them. Such conditions created a unique habitat that later became the foundation for the evolution of more complex forms of life. These early seas served as the stage for nature's first experiments, with each drop of water holding the potential for the history of future life. Research shows that the salt content in these bodies of water was significantly lower than in modern oceans, which also influenced the composition and structure of the primary ecosystems. In the primary oceans of Earth, complex chemical reactions took place, which can be imagined as a boiling cauldron where water interacted with minerals emerging from the planet's crust and gases present in the atmosphere. These oceans, much like giant natural laboratories, were the site of thousands of continuous reactions that led to the formation of new compounds and substances. For instance, water passing through rocks and minerals dissolved them, and the elements contained within combined with gases like carbon dioxide and ammonia, creating a unique chemical environment. During this period, starting around 4 billion years ago, water temperatures could reach high values, enhancing the activity of chemical reactions. All this occurred under conditions where solar radiation was significantly lower than today, and the atmosphere was rich in various gases that provided the necessary conditions for chemical evolution. In such conditions, these simplest organic molecules were formed, laying the foundation for future life. The work of scientists like Stanley Miller, who in 1950 conducted the famous experiment on the synthesis of organic compounds from inorganic substances, underscores the importance of these processes. He demonstrated how, under controlled conditions, amino acids, building blocks of proteins, which play a key role in living organisms, could be obtained. The oceans, filled with elements and compounds, became an ideal environment for these reactions, and their unique chemical composition contributed to the creation of complex organic molecules. This process occurred over millions of years, and through various chemical interactions, structures were formed that eventually became the basis for the first forms of life on Earth. While the oceans were filled with these molecules, active processes transformed them into more complex elements, creating not only conditions for life, but also precursors of the organisms that later inhabited our planet. By studying geological layers and samples obtained from deep-sea drilling, scientists find traces of these early chemical processes, allowing them to draw conclusions about how life began on Earth. Each new layer of oceanic sediments contained evidence of these ancient processes, and with each discovery, we move closer to understanding how complex molecules could organize into living systems. During the same period when the primary oceans were forming, significant tectonic processes occurred on Earth, which also influenced the chemical composition of oceanic water. At the bottom of the primary oceans, there existed hydrothermal sources that can be considered true oases of heat and chemical activity. These sources were represented by cracks in the ocean floor from which hot water, rich in minerals, was ejected, creating unique ecosystems. For instance, in 1977, an expedition led by scientist Robert Ballard discovered hydrothermal sources on the Galapagos Ridge, where the water temperature reached 300 degrees Celsius. The water emerging from these cracks was rich in minerals such as hydrogen sulfide, zinc and copper, contrasting with the cold, nutrient-poor water surrounding these underwater smokestacks. These smokestacks released streams of dark, mineralized water, creating a striking sight when hot water mixed with cold, forming clouds reminiscent of smoke. This process not only created a visual contrast between two worlds, but also contributed to the formation of unique ecosystems around the sources. For example, organisms such as tube worms and giant clams were found in the studied areas, which had adapted to extreme conditions, finding food in hydrogen sulfide. These organisms became the basis for complex food chains, challenging the traditional view that life on Earth can only exist in the presence of sunlight. Hydrothermal sources also played a significant role in the carbon cycle, as they facilitated the release of carbon dioxide into the ocean and atmosphere. Scientists such as Dr. John L. Carruthers assert that these sources could have been the first places where life on Earth originated. Remarkably, the temperature and chemical composition of the water in these sources created unique conditions, distinct from the surrounding environment, allowing scientists to better understand how life might have originated on other planets, such as Europa, Jupiter's moon. Notably, hydrothermal sources not only supported life but also influenced the geochemistry of the oceans, altering the composition of oceanic water over millions of years. Formation of the first continents began approximately 3.5 billion years ago, when the Earth's surface began to cool and lighter rocks started to rise to the surface of the mantle. These areas of lighter crust, known as continental plates, floated on the liquid mantle, much like rafts on water. Initially, the Earth consisted of scattered fragments, small archipelagos, which gradually came together to form larger land masses. During this time, the shape of the land was unstable. Land masses constantly changed their outlines due to tectonic processes and volcanic activity. Volcanic islands emerged as a result of mantle flow, creating temporary land areas that could disappear as quickly as they appeared. These young continents were much smaller than today's continents and lacked vegetation, as the conditions on the planet were far from the warm and humid climate we observe today. Temperatures were high, and the atmosphere contained many toxic gases, making life on the surface practically impossible. Constant volcanic activity created new mountain ranges, while other land areas could sink under pressure, distorting and altering their outlines. Over millions of years, as a more stable crust formed, these areas began to unite into larger continents, but at that time they were dynamic and changeable formations. These processes were crucial for the geological foundation of our planet, as it was then that conditions began to form, which later led to the emergence of life. During this period, signs of continental margins also began to appear, where some land areas rose while others sank, creating complex relief forms that later became the basis for modern continents. In the early stages of Earth's existence, tectonic processes were extremely intense and dynamic. The Earth's crust, composed of numerous fragments, was in a state of constant motion, forming a peculiar mosaic where each element could change its position. This continuous process was driven by internal planetary forces that were significantly stronger due to the greater amount of heat generated by the decay of radioactive elements and the residual heat from Earth's formation around 4.5 billion years ago. For instance, in those distant times, temperatures in the mantle could reach over 1,000 degrees Celsius, facilitating the melting and upward movement of magma. As a result of this movement, massive mountain ranges and basins were formed, along with volcanoes that erupted lava and created new crustal areas. Each time crustal fragments shifted, they not only altered the landscape but also influenced climatic conditions, creating new ecosystems. Such tectonic processes led to the formation of oceans and continents, and their constant movement shaped new geographical forms that were in eternal struggle for space. Imagine Earth's surface as a vast mosaic painting where each fragment constantly changes its pattern, while beneath them, forces capable of moving and colliding gigantic plates rage. This dynamism not only created landscape diversity but also influenced the development of life on the planet, as new continents and oceans provided conditions for the evolution of various species. It is important to note that such tectonic movements occurred with greater frequency and intensity than today, resulting in the formation of massive earthquakes and volcanic eruptions that changed the face of Earth. As the planet cooled and its internal heat decreased, tectonic processes became less active, but their effects continue to be felt today. Over this long and complex process, which lasted millions of years, our planet acquired the unique appearance we can observe today. The tectonic movements that occurred in ancient times were foundational in shaping modern continents, and their traces can be seen in geological layers that have recorded millions of years of history. In particular, in some places, layers containing fossils can be found, which confirm changes in climate and ecosystems caused by these movements. Each crustal layer carries a history written in stone and is a testament to the colossal forces that acted on Earth millions of years ago. Subduction is a process that involves one tectonic plate descending beneath another. This slow but powerful process can be compared to a giant conveyor belt that returns surface material back into the planet's interior. The most well-known example of subduction can be observed at the boundary between the Pacific and North American plates, where the Pacific plate slowly descends beneath the North American plate, creating impressive geological formations such as mountain ranges and volcanoes. This process can take millions of years, with the rate of descent being just a few centimeters per year, giving the illusion of geological calm while hiding the immense forces at work deep within the Earth. When one plate descends beneath another, it does not simply disappear. Instead, it gradually heats up and melts into the mantle, forming magma that can later erupt onto the surface as volcanoes. Volcanic activity associated with subduction is one of the most striking examples of this process. For instance, in the region of the Mauna Loa volcano on Hawaii, where subduction occurs, there has been recorded significant volcanic activity that has led to the formation of large lava plains. Subduction is also responsible for the creation of deep oceanic trenches, such as the Mariana Trench, which is the deepest point on the planet, reaching depths of over 10,900 meters. Research shows that as a result of subduction, complex geological structures such as accretionary wedges are formed. These structures are made up of accumulations of sediments and magmatic materials that form at the plate boundaries. These structures can be very complex and diverse, highlighting the variety of processes involved in subduction. Scientists like Dr. Christopher Hawkins from the University of California study these processes using modern technologies such as seismic research and satellite observations to better understand how subduction influences the formation of the Earth's crust. There are many examples where researchers have documented how one tectonic plate slowly slides beneath another, leading to the formation of new mountain systems and changes in the landscape. For example, the Andes mountain system in South America was formed over a long period of subduction that continues to this day, forcing scientists to re-evaluate our understanding of mountain formation. It is important to note that although the process of subduction may seem slow, it leads to significant changes at the planetary level, including earthquakes and volcanic eruptions that can devastate entire regions. In particular, earthquakes caused by plate movements can reach magnitudes of over 9, as seen in Japan in 2011, when an earthquake off the coast of Tohoku triggered a tsunami with catastrophic consequences. It is crucial to understand that subduction is not just a geological process, but one of the key factors shaping our planet and its ecosystems. Research shows that without subduction, Earth would be entirely different. Without mountains, volcanoes, and even the familiar ocean floor that is created by this process. Subduction is a powerful mechanism that not only determines geological activity, but also influences climate conditions, affecting life on the Earth's surface. The formation of the first mountain ranges on early Earth occurred as a result of the collision of tectonic plates, leading to significant deformations of the crust. Around 2.5 billion years ago, during the Archean period, processes began that laid the foundation for the formation of mountain ranges. When two sections of the crust collided, their surfaces were compressed and pushed upwards, forming low, sharp ridges of dark, volcanic rock. These primary mountains, known as proto-mountain systems, were not the grand peaks of today's Alps or Himalayas, but rather low, sharp formations that gradually rose above sea level. At that time, there was no erosion characteristic of modern mountains, as rivers and glaciers had not yet begun to form. Only wind and rain affected these newly born peaks, smoothing their sharp edges. The process of mountain formation continued for millions of years, and it was during this time that the first volcanic eruptions occurred, adding new layers of rock to the surface. The establishment of mountain systems did not conclude in the Archean period, but it was then that the first stages began, which later led to the formation of extensive mountain ranges such as the Appalachians, the Rocky Mountains, and others. At the same time, geological structures such as shields and platforms were formed, which became the basis for future continents. These primary formations witnessed not only tectonic processes, but also changes in climate and ecosystems that developed on Earth. For example, during the Mesozoic era, mountain systems continued to transform, becoming increasingly higher and more complex, and their formation contributed to the creation of unique ecosystems. The appearance of new plants and animals also depended on these geological changes, highlighting the connection between mountain formation and the evolution of life on Earth. The initial mountain formations, such as the Appalachians, emerged around 300 million years ago as a result of the collision of tectonic plates, and their age indicates the time when Earth was just beginning to take on its modern appearance. As a result of this prolonged process, we can trace not only the geological history of our planet, but also the evolution of its ecosystems. The changes in the early Earth's atmosphere were a captivating process that unfolded over hundreds of millions of years. The initial atmosphere, formed as a result of volcanic activity and the release of gases from the planet's interior, was extremely aggressive and toxic. Volcanic eruptions that occurred around 4 billion years ago released massive amounts of water vapor, carbon dioxide, and other volatile substances. These gases, interacting with the young oceans, began to create more complex atmospheric conditions. Gradually, as the Earth's surface cooled and water vapor condensed, oceans formed, which began to absorb carbon dioxide and other components of the primary atmosphere. This process can be likened to the slow breathing of the planet. A dense and poisonous envelope gradually became less dense and toxic, allowing for a clearer and more transparent sky. With each million years, the atmosphere lost its aggressiveness and hints of blue began to appear on the horizon. It is crucial to note that these changes did not occur instantaneously. This was a lengthy and complex process involving geological phenomena such as plate tectonics and erosion, as well as the biological influence of the first single-celled organisms, which began to produce oxygen through photosynthesis. From a biological perspective, the formation of the atmosphere can be seen as a symbiosis between the planet and life, where each played its role in creating conditions for the emergence of multicellular organisms. Thus, over millions of years, Earth, like a living being, slowly and deeply breathed, changing its appearance and preparing the ground for future biodiversity. These changes laid the foundation for the formation of the ozone layer, which began to protect the Earth from harsh ultraviolet radiation, creating a safe environment for life. Ultimately, the atmosphere, transformed into a more dynamic and multi-layered structure, became a key element in maintaining the balance of the planet's climate and ecosystems, opening the door to the evolution of more complex forms of life. Within this long process, various stages can be distinguished, such as the transition from anaerobic to aerobic conditions, which occurred around 2.5 billion years ago, when the level of oxygen in the atmosphere began to significantly increase due to the activity of cyanobacteria. The process of weathering, which began billions of years ago, has laid the foundation for the formation of the modern composition of the atmosphere and the Earth's crust. Water falling on various rocks does not simply flow but actively interacts with them, entering into complex chemical reactions. For example, raindrops containing carbon dioxide form carbonic acid, which, when it falls on limestone, dissolves it, extracting calcium and carbon dioxide into the solution. This process, known as karst weathering, is particularly evident in regions such as the karst areas of Slovenia, where it leads to the formation of vast underground caves and unique landscapes. Over millions of years, these chemical reactions have not only altered the rock itself, but also the atmosphere, bringing new elements and compounds to the surface, which then become part of the soil and water. Water, like a living organism, dances with the rock, dissolving it and moving minerals, while the air, in turn, introduces oxygen into this process, leading to the formation of oxides such as iron and aluminum, which then settle as deposits. This endless cycle of interaction between water, rock, and atmosphere occurs wherever water comes into contact with the Earth's surface, creating a global geochemical cycle that shapes our world. On other continents, such as South America, in the conditions of tropical rainforests, weathering occurs more intensively due to high levels of precipitation and temperatures, resulting in the formation of diverse soils, such as laterite soils rich in iron and aluminum. This process not only changes landscapes but also affects living organisms, as changes in soil composition directly impact ecosystems. For example, in Africa, where weathering occurs in a dry climate, desert landscapes form, where the survival of plants and animals depends on rare rainfall. As a result, weathering becomes not just a geological process, but a crucial factor that shapes the ecological conditions on the planet, creating a complex network of interactions between land, water, and atmosphere. These phenomena occur over millions of years, demonstrating how slowly but surely the appearance of our planet changes under the influence of simple but powerful natural forces. As a result of this interaction, the Earth's atmosphere becomes increasingly rich in oxygen, while the level of carbon dioxide decreases, creating conditions for the development of life on the planet. The formation of the primary ozone layer marked a new stage in Earth's history, providing protection for developing life and creating unique conditions on the planet. This layer began to form approximately 2 billion years ago when molecules of oxygen, released by photosynthetic organisms, started interacting with ultraviolet solar radiation. Solar rays, penetrating the upper layers of the atmosphere, activated oxygen molecules, causing them to break down into individual atoms. As a result of these reactions, ozone molecules, consisting of 3 oxygen atoms, were formed. This process can be compared to the construction of an invisible shield that gradually formed high above Earth's surface, creating a protective screen against harmful ultraviolet radiation that could have destroyed life on the surface. Initially, the ozone layer was quite thin and ineffective, but as the concentration of ozone increased, its protective properties significantly improved. Research shows that with each million years, this layer became denser and more stable, allowing life on Earth to develop without fear of solar rays that could damage the DNA of organisms. The importance of this process is difficult to overestimate. It was the formation of the ozone layer that made it possible for more complex forms of life, including the first multicellular organisms, to colonize land. Thus, the formation of the ozone layer became one of the key factors contributing to the evolution of life on the planet. It is also important to note that this process continued over millions of years and contributed to the development of ecosystems that we observe today. Scientific research conducted in recent decades confirms that without the ozone layer, life on Earth would have been completely different and perhaps would not have existed at all. In the process of forming the ozone layer, not only oxygen molecules were involved, but also other gases such as water vapor and carbon dioxide, which also played a role in creating conditions for life. At the dawn of life on Earth, approximately 4 billion years ago, a remarkable chemical evolution took place in the primary oceans. Simple molecules such as hydrogen, carbon, and oxygen were abundant, interacting with each other in conditions far removed from the modern world. Imagine a primordial soup where molecules danced, bonding and breaking apart, forming increasingly complex chains. This dance was catalyzed by various energy sources such as lightning, which could reach temperatures above 1,000 degrees, or ultraviolet radiation penetrating a thin atmosphere. For instance, in laboratory conditions, scientists like Stanley Miller in 1953 demonstrated that such conditions could lead to the formation of organic molecules necessary for life, even in an artificial broth. There was a spontaneous organization of simple compounds into more complex structures, which was a crucial step for the further development of life. This process was not random. It was governed by physical and chemical laws that directed molecules towards the formation of increasingly complex and stable forms. For example, under various conditions on Earth, polymers could form, which later became the basis for more complex biomolecules. The role of minerals, such as clay, was also significant, as they could serve as catalysts for these reactions, facilitating the formation of long chains resembling threads. Given that Earth had vast oceans at the time, these processes could occur in various geographical zones, from hot springs to cold depths, expanding the range of possibilities for chemical evolution. Thus, in this primordial ocean, the chaotic movement of molecules gradually transformed into organized structures that eventually became the precursors of life, creating conditions for the emergence of the first simple organisms. With each new interaction, life became more likely, and energy was the catalyst for this process. In such conditions, as in the turbulent volcanic activity or the strikes of lightning, reactions occurred that gradually created small organic molecules, such as amino acids and sugars, which became the foundation for subsequent biochemical processes. These processes took place over at least 1 billion years before the first life capable of self-replication appeared on the planet. The RNA world hypothesis offers an intriguing perspective on the possible stages of pre-biological evolution, during which RNA molecules could have performed two key functions: storing genetic information and catalyzing chemical reactions. These molecules, composed of nucleotides, are not only capable of encoding information, as DNA does, but also of acting as ribozymes, which accelerate chemical reactions. Research conducted in the early 2000s by a group of scientists led by Dr. Ron Evans of the University of Washington showed that RNA molecules could form complex structures that provided the necessary stability and reactivity, allowing them to interact with other chemical compounds. These properties make RNA the first candidates for the role of living entities on the border between non-living and living matter. Studies conducted in 2001 demonstrated that some ribozymes can replicate themselves, creating the prerequisites for self-reproduction. This suggests that the origin of life was the result of a long chemical evolution, rather than a random event. Scientists such as Dr. Sidney Altman, a Nobel laureate in chemistry, assert that RNA molecules played a key role in the formation of the first living organisms, supported by their ability to self-replicate and catalyze in conditions similar to those that existed on early Earth. Thus, RNA molecules become central figures in this hypothesis, linking chemical evolution with biological evolution, asserting that they could have formed the basis for complex biochemical systems that later evolved into primitive life forms. This process likely occurred over millions of years as RNA molecules interacted with their environment, changing and adapting to conditions allowing them to evolve into more complex structures. Research conducted in 2006 showed that under conditions mimicking early Earth, RNA molecules can form more complex systems capable of self-reproduction. Therefore, the RNA world hypothesis opens new horizons in understanding how life could have emerged on our planet and which molecules could have been the first steps on this path. The formation of the first cellular membranes from lipid molecules was one of the key stages in the evolution of life on Earth. Water, as a universal solvent, played a central role in this process. Lipids, molecules with hydrophobic and hydrophilic ends, possess unique properties that allow them to spontaneously organize in an aqueous environment. When lipids enter water, the hydrophilic, water-loving parts strive to interact with water molecules, while the hydrophobic, water-repelling parts try to avoid contact with it. This leads to the formation of double layers, where the hydrophobic ends are inside, protected from water, and the hydrophilic ends are on the outside, interacting with the aqueous environment. This self-assembly process results in the formation of microscopic vesicles known as liposomes, which are precursors to cellular membranes. Each such vesicle creates a thin envelope that separates the internal contents from the surrounding environment, forming a protected space. This separation is critically important because it allows for more complex chemical reactions necessary for life. Within these membranes, metabolic reactions, protein synthesis, and other processes can occur which were previously impossible in an open environment. For instance, research conducted in 2003 by a group of scientists led by Dr. John Myers from the University of Cambridge showed that such membranes can retain necessary molecules and ions, creating favorable conditions for the development of primitive life forms. The creation of these membranes laid the foundation for the further evolution of cells, including the emergence of more complex structures and systems. It is worth noting that such simple cellular membranes can serve as a basis for the formation of more complex cells that appeared later, including prokaryotes and eukaryotes. These processes took place on Earth more than 3 billion years ago when the conditions on the planet were entirely different, and it was then that life began its long journey towards diversity, which we observe today. Changes in the chemical composition of Earth's primary atmosphere, which occurred approximately 3 billion years ago, served as a catalyst for the formation of the first protocells, which are the precursors to modern living organisms. In those conditions, when chaos reigned on the planet, molecules began to interact with each other, forming more complex structures. This process was akin to a subtle whisper in the ocean of chemical reactions, where each new molecule, joining with another, gradually acquired properties that we today associate with life. Protocells did not have clear boundaries, but their molecular systems began to exhibit the ability to self-replicate, marking the first step towards the emergence of life. This phenomenon did not occur instantaneously, but developed over millions of years, blurring the line between the non-living and the living. Information about such processes can be found in the works of scientists studying abiogenesis, such as Stirling and Lipson, who describe how simple molecules, such as amino acids and nucleotides, could combine to form more complex structures, contributing to the formation of the first cell membranes. These molecules did not merely exist but actively participated in metabolic exchange with the surrounding environment, adapting to changing conditions. Over millions of years, these molecular systems, penetrating into newly formed energy flows and chemical reactions, created an environment conducive to further life development. The phenomenon known as chemical evolution became the foundation for the appearance of increasingly complex forms of life, including bacteria, which first appeared around 3 billion years ago. These microorganisms, being the simplest representatives of living beings, began to actively change the Earth's atmosphere by releasing oxygen during photosynthesis. As a result, a global transformation began on the planet, which in turn created conditions for the appearance of multicellular organisms. Scientific research shows that it was during this period, around 2.5 billion years ago, that the level of oxygen in the atmosphere began to significantly rise, serving as a catalyst for further evolutionary processes. This process was not simply linear, but resembled a complex dance of molecules where each new form of life influenced the surrounding environment, creating conditions for the appearance of subsequent generations of living organisms. Scientists like Craig Venter actively studied genomic sequences to understand how these early forms of life could adapt and survive in conditions that were far from favorable. It is important to note that each new discovery in this field not only deepens our understanding of the origin of life, but also underscores the significance of those first steps that molecules took, striving for self-replication and interaction with the surrounding environment. Stromatolites are remarkable and ancient testaments to microbial life on Earth, dating back over 3 billion years. These layered structures form due to the activities of cyanobacteria and other microorganisms in shallow seas, where they create small mounds on the floors of the primary oceans. Stromatolites grow incredibly slowly, sometimes by only a few millimeters per year, and can reach substantial sizes. For instance, in the Australian Shark Bay, there are stromatolites that are over 3 million years old, making them some of the oldest inhabited structures on the planet. These formations consist of microscopic cells that, by stretching their layers, capture sedimentary particles, forming what are essentially cakes of calcium and organic remains. Stromatolites serve as the first example of an ecosystem where microorganisms interact with each other, forming complex communities. In these ecosystems, cyanobacteria played a crucial role in producing oxygen, ultimately leading to changes in Earth's atmosphere that allowed more complex forms of life to evolve. Research conducted by scientists like Dr. Mary Bailey from the Institute of Geology shows that stromatolites not only preserve information about ancient atmospheres and climates, but also serve as indicators of changes in ecosystems. For example, in places where stromatolites continue to grow, they can be observed reacting to changes in oxygen levels and water salinity. As a result, these structures are not just fascinating geological formations, they are also important archives of Earth's biological and climatic history, preserving traces of the interactions between microorganisms and their environment over millions of years. Stromatolites are found not only in Australia, but also in places like the Bahamas and the Mexican Gulf, where they continue to be studied to understand the evolution of life on our planet. Ancient cyanobacteria, which began to exist approximately 3 billion years ago, were the first organisms capable of performing photosynthesis, using solar energy to produce organic compounds from carbon dioxide and water. This process, known as oxygenic photosynthesis, involved converting light into chemical energy, which was then used to synthesize glucose, while oxygen was released as a byproduct. Unlike other photosynthetic organisms, such as green plants, cyanobacteria used specific pigments like chlorophyll A, allowing them to efficiently absorb light waves of different lengths. This ability to photosynthesize not only provided cyanobacteria with a source of food, but also began to radically alter the chemical composition of Earth's atmosphere. Imagine billions of microscopic organisms slowly but surely filling the atmosphere with oxygen, while carbon dioxide is transformed into organic matter. This process led to what is known as the oxygen catastrophe, an event that occurred around 2.5 billion years ago when the level of oxygen in the atmosphere began to rise, reaching levels that allowed for the emergence of new forms of life. Cyanobacteria, such as Nostoc and Anabaena, played a key role in this process, forming colonies that could create dense mats or films on the surface of water, thereby increasing their efficiency in capturing sunlight. As a result of such active photosynthesis, Earth's atmosphere began to change significantly, and oxygen became the main component necessary for the existence of aerobic organisms. This transition to an oxygen-rich atmosphere opened up new ecological niches, facilitating the evolution of more complex forms of life. Thus, cyanobacteria became not just organisms, but true architects of our planet, creating conditions for the life we know today. They also made significant changes in the oceans, creating conditions for the development of other photosynthetic organisms, such as algae. These changes would not have been possible without the ability of cyanobacteria to photosynthesize, making them some of the most important organisms in Earth's history. Oxygen produced by photosynthesis by organisms gradually filled the Earth's atmosphere, changing its color and composition. This process, known as the Great Oxygenation Event, was a turning point in the history of our planet. For millions of years, cyanobacteria living in shallow ocean waters produced oxygen through photosynthesis, using sunlight to convert carbon dioxide and water into organic matter and oxygen. Gradually, oxygen, which was barely present in the atmosphere before, began to accumulate, creating conditions for changes in ocean chemistry. Initially, oceans became less acidic, and then, due to interaction with dissolved iron, they began to acquire the characteristic blue color we see today. This process led to the formation of sedimentary rocks, such as iron formations, which contain oxidized iron, indicating high oxygen levels in the water. However, oxygen, which was a source of life for many organisms, proved toxic to most of the existing life forms, such as anaerobic bacteria, which could not survive in the conditions of high oxygen levels. This created a paradoxical situation. Many organisms went extinct, but at the same time, oxygen opened up new evolutionary possibilities for those who could adapt to the new conditions. For example, the emergence of aerobic respiration allowed organisms to more efficiently use energy, facilitating their rapid development and diversification. As a result, life on Earth began to take on new forms, including the ancestors of modern plants and animals, which could use oxygen for their biochemical processes. This event not only changed the atmosphere but also determined the evolution of life on the planet, creating conditions for the appearance of complex organisms. Over millions of years, oxygen produced by simple life forms changed the planet, making it suitable for more complex forms of life. Oxygen became the basis for the formation of the ozone layer, which protects living organisms from harmful ultraviolet radiation. Red-banded iron formations are unique geological records that attest to the oxygenation of the oceans, which occurred approximately 2.5 billion years ago. These striped rocks, composed of alternating layers rich in iron and silica, formed on the ocean floor where conditions were ideal for the reaction of dissolved iron with oxygen released by photosynthetic microorganisms. As a result of this reaction, iron oxides were formed which settled on the ocean floor, creating the characteristic red and brown hues that we observe today. These layered rocks can reach thicknesses of several hundred meters and extend for tens of kilometers in length, making them significant objects of study for geologists and paleontologists. For instance, formations such as the banded iron formations in the Pilbara region of Australia, which contain rich deposits of these iron formations and date back to the Archean period, are of particular interest. These geological layers serve as a kind of fossil record inscribed in stone, chronicling the great transformation of the planet when the level of oxygen in the atmosphere began to significantly increase. Research conducted by scientists like Dr. Daniel Blake of the University of California, Berkeley, has shown that the presence of these layers indicates that the oceans underwent massive changes, leading to the emergence of a new era, the oxygenation event. Scientific data confirm that these processes not only resulted in the oxygenation of the oceans, but also led to profound changes in ecosystems, driving mass evolution of life forms. These rocks contain trace isotopes that assist scientists in reconstructing ancient environmental conditions. For example, analysis of carbon and sulfur isotopes in these layers can reveal how the biosphere changed and which organisms were dominant during that time. Consequently, red-banded iron formations are not only geological artifacts, but also a crucial key to understanding the evolution of Earth and life on it. The snowball Earth hypothesis suggests that around 600 million years ago, our planet could have been almost completely covered in ice, including the oceans, which turned into frozen deserts. This phenomenon could have been caused by significant changes in the composition of the atmosphere, particularly a decrease in the level of carbon dioxide and an increase in oxygen, leading to global cooling. As a result, the surface temperature of Earth dropped to critical levels and the waters of the oceans froze, creating massive ice shields that stretched from the poles to the equator. Imagine a planet encased in an icy shell with rare oases of open water forming around volcanic islands, where hot geysers and volcanic eruptions created small ecosystems capable of supporting life. These conditions were extremely harsh for early forms of life, which likely existed in these isolated oases. Nevertheless, such a harsh environment also played a role as an evolutionary filter. Only the most adapted organisms could survive and adapt to these extreme conditions. For instance, at this time, organisms similar to multicellular algae and bacteria could have existed, which developed mechanisms to protect against cold and UV radiation. It is important to note that it was under the conditions of snowball Earth that significant changes in the evolution of living beings took place, ultimately leading to the appearance of more complex forms of life, such as the first animals that began to colonize the oceans. These early organisms were the predecessors of modern forms of life, and their existence under the ice cover was a true evolutionary feat. Scientists such as Professor David G. Bott and his team studied geological layers that testify to periods of planetary glaciation, as well as how changes in climate affected the biosphere. By comparing data on the composition of carbon isotopes, they were able to determine that the level of carbon dioxide in the atmosphere during snowball Earth had significantly decreased, which could have led to such catastrophic changes in climatic conditions. As a result, the planet experienced some of the most extreme changes in its history, and these conditions formed the basis for the evolution of life as we know it today. The conditions on snowball Earth also created unique geological and climatic conditions that contributed to the formation of minerals such as shales and limestones. The first eukaryotic cells appeared around 2 billion years ago and marked a true breakthrough in biological evolution. These more complex cells differed from their predecessors, the prokaryotes, by having a nucleus and organelles, which can be likened to the transition from a single-room apartment to a multi-room apartment, where each room serves a specific function. This new level of organization led to the emergence of a complex structure within the cell, allowing it to carry out multiple processes simultaneously, much like a miniature city with various districts. In such a cell, for example, the nucleus can be compared to a city hall, where important documents are stored and key decisions are made, while mitochondria function as power plants, providing energy for all internal processes. This step in evolution paved the way for multicellularity, which became the foundation for the emergence of all modern organisms, from simple algae to complex mammals. The appearance of eukaryotes enabled a wide range of metabolic processes and cell specialization, leading to the formation of tissues and organs. An example of this diversity is seen in plants, animals, and fungi, all of which originated from these first eukaryotic cells. As a result, eukaryotes became the basis for a complex hierarchy of life on Earth, where each group of organisms occupies its niche in the ecosystem. Over time, these cells began to form multicellular organisms, giving rise to the first multicellular forms of life, such as algae and simple animals, which appeared on the planet around 600 million years ago. The theory of endosymbiosis, proposed in the mid-20th century by American biologist Lynn Margulis, describes how some organelles of eukaryotic cells, such as mitochondria and chloroplasts, originated from bacteria that were engulfed by other cells, but not digested. Instead, they began to coexist in symbiosis. This discovery was a true revolution in our understanding of cellular biology and evolution. Imagine a primitive prokaryotic cell engulfing a more energy-efficient bacterium. Instead of destroying it, the cell begins to benefit from its presence, providing protection and nutrients, and in return receives energy in the form of ATP, which allows the cell to survive and develop into more complex structures. This process was not a one-time event. Such unions could occur repeatedly, creating increasingly complex cellular organisms. For example, mitochondria, responsible for cellular respiration, are structurally and genetically similar to modern alpha proteobacteria, confirming their ancient origin. Similarly, chloroplasts, which carry out photosynthesis in plants, share many characteristics with cyanobacteria. This cooperation at the cellular level is a vivid example of how competitors can become allies, forming a single entity, which significantly accelerates evolutionary processes. Such symbiotic relationships not only enhance survival but also open new pathways for adaptation to the environment. A key aspect of the theory is that endosymbiotic events likely occurred repeatedly over billions of years, allowing the emergence of the diverse forms of life we observe today. For instance, according to scientists, around 1 billion years ago, a key integration between eukaryotes and photosynthetic organisms occurred, leading to the emergence of the first multicellular algae. This discovery sheds light on questions related to the origin of complex life on Earth, demonstrating that cooperation and resource exchange at the cellular level could have been the foundation for the emergence of the biodiversity of the biosphere. It is important to note that during this evolution, not only did cell sizes increase, but also the complexity of their functions, ultimately leading to the formation of multicellular organisms and ecosystems that we know today. Endosymbiosis became the basis for the development of new metabolic pathways and exchange of substances, which in turn contributed to the acceleration of evolutionary changes. The first multicellular organisms appeared on our planet approximately 800 million years ago, during a period known as the Ediacaran period. These primitive beings were neither plants nor animals, but rather something intermediate, floating in ancient seas. Unlike single-celled organisms that existed before them, multicellular organisms began to form colonies where each cell became specialized and performed specific functions. For instance, some cells were responsible for food intake, others for protection against external threats, and still others for reproduction. This marked an important step in evolution, as it allowed the organism to function more efficiently and adapt to various environmental conditions. As a result, such colonies could reach significant sizes, sometimes exceeding several meters in length. For example, fossilized remains of such life forms as Dickinsonia, discovered in Australia, indicate that these organisms could reach lengths of up to 1 meter and were covered with a soft body with characteristic ribs. These primitive colonies floated in marine water, allowing them to freely move and search for food, feeding on microscopic algae and bacteria. Despite their simplicity compared to modern forms of life, multicellular organisms became the foundation for further evolutionary development and diversity, which we observe today. This was a time when life on Earth was just beginning to explore the complexity of multicellularity, and these early organisms became the predecessors of all subsequent forms of life, from marine creatures to terrestrial plants and animals. Their existence opened new horizons for biological evolution and diversity, leading to the emergence of more complex multicellular forms that ultimately filled the oceans and land. The Ediacaran biota, which existed approximately from 600 to 500 million years ago, represents a mysterious and unique stage in the history of life on Earth. These earliest known multicellular organisms found in places like Ediacara in Australia and Nunavut in Canada were flat, soft-bodied creatures resembling leaves or feathers. Their form and structure were absolutely unlike anything we observe today. Imagine the ocean floor covered with these strange beings, gently swaying in the currents like underwater plants. Unlike modern organisms, Ediacarans did not have hard skeletons and were not predators, creating a completely different ecological balance. For example, the well-known species Dickinsonia, up to a meter long, had an oval shape and was covered with segmented patterns that likely served for respiration and nutrient absorption. These organisms did not leave behind traditional fossils, making their study difficult, but finds like well-preserved impressions on shales allow scientists to make inferences about their appearance and function in their ecosystems. Research suggests that the Ediacaran biota may have been the first attempt by nature at multicellularity, and although they existed in a world without predators and intense competition, their existence raises many questions about how life could have evolved in conditions completely different from today's. Scientists like Derek Brown point out that these creatures could have been predecessors of more complex forms of life, such as trilobites and other invertebrates that appeared later. Their unusual forms and structure reflect our own limitations in understanding life. They existed in a time when the rules of the biological game were entirely different. These organisms lived before the appearance of hard skeletons, making them complex to classify and understand. Their unique adaptations to their environment show how life could have evolved completely differently in the absence of familiar conditions. These enigmatic, slow and soft creatures filled the ocean depths, leaving behind only impressions and mysteries that still lack definitive answers. Scientific research continues, and each new discovery can change our understanding of these ancient beings and their role in the evolution of life on the planet. In recent years, a group of researchers from the University of Hartford has found new samples of Ediacaran biota that may provide additional information about how they interacted with their environment. Studying the journey of our planet makes it impossible not to be amazed at how Earth, once a fiery sphere, has passed through fire, water, and ice to become a home for diverse forms of life. Imagine how, at the beginning of its existence, Earth was like a hellish cauldron, with temperatures reaching 1,000 degrees and an atmosphere composed of toxic gases. Over time, as the planet cooled, it formed a crust and the first oceans, leading to the evolution of conditions necessary for the emergence of life. These oceans, the true cradles of the first microorganisms, were filled with chemical compounds from which, as is believed, the first amino acids arose. Scientists suggest that the formation of the simplest organisms could have occurred in deep-sea hydrothermal vents, where hot water combined with minerals to create an ideal environment for the emergence of life. This transition from non-living matter to living organisms may have been one of nature's most extraordinary miracles. However, the path to complex forms of life was long and arduous. About 2 billion years ago, Earth experienced a significant shift. Organisms capable of photosynthesis appeared, producing oxygen, which completely changed the planet's atmosphere. This oxygen became the basis for the emergence of multicellular life and ultimately animals. As time passed, Earth went through numerous catastrophic events, from mass extinctions to ice ages, each leaving its mark on ecosystems. Each of these events created unique conditions in which various species evolved. For example, about 66 million years ago, a mass extinction likely caused by an asteroid impact led to the disappearance of dinosaurs and paved the way for the emergence of mammals. This demonstrates that life on the planet is not just statistics, it is a unique story filled with dramatic turns. Each species that appears on the stage is the result of an endless process of adaptation and survival. This history, preserved in the layers of the Earth, allows us, modern inhabitants of the planet, to study and understand how life has developed, how it has reacted to changes, and how we, in turn, should cherish this fragile heritage. Lying in our beds, we can ponder the ancient seas that once covered Earth, the first glimpses of life breaking through murky waters, and how all this led to what we have today. So let us not forget the value of our world and how remarkable it is that we can study its history. Night envelops us, bringing with it peace and deep dreams, where ancient creatures continue to swim in their seas and the first forms of life strive towards the light.